on this computer. I clicked the record button. I think it's recording. Okay. So we now apply a non-exact sequence to this thing. So this is kj. I really should have chosen like a different letter, but this is j. So kj maps into ij, maps into kj plus 1. We know we built all these sequences before. Those are, again, just these triangles facing down. By applying the non-exact sequence to these, we generically find what I mentioned earlier, that if we raise the cohomology, then we lower we raise the dimension of the cohomology, we lower the dimension of the k's, or vice versa. So remembering that f is k naught, if we want to find the ith cohomology of f, we write it as the ith cohomology of k naught, and we just keep raising the k dimension, and we keep lowering the h dimension till we get down that is h1 of k to the I minus 1. And now we have to actually calculate this thing, but it's only the first cohomology, so it shouldn't be that hard, right? So we note that this short exact sequence we had will extend to, well, this is one of our short exact sequences, but we choose this one so we can calculate the cohomology, because conveniently, if we choose this short exact sequence, when we extend it, we get this long exact sequence, where this one is going to be 0 again, this term here, the second h1 term, because I is an injective object. So as we had before, we can calculate h1 by, it is the, well, it's defined to be the co-kernel of this map right here, which means it is this object right here, mod the image of this map, this arrow. This is, again, I'm assuming, one might complain that with co-kernels, I've been assuming co-kernels can be written as quotients through all this. I'm appealing to Freyd-Mitchell here, which says that you can do that. And I looked through all the stuff with Freyd-Mitchell. I can talk about that next time, actually. I looked into Levi's question last time, but I think that's something we should reserve for when Ada talks about it, and I'll do a little bit more research. But suffice to say, part of what you can do with Freyd-Mitchell is you can set up a restricted setting in which you can prove that this generically holds in the original setting. You can just always assume co-kernels are quotients when doing diagram chases with abelian stuff, and stuff works out fine. So since it's a left exact functor and the global sections functor, remember it was adjoint to what we constructed its adjointness last time. And the sequence here is exact by definition. We know that the sections of ki is the kernel of this map. Remember, basically we're saying that what this post is saying is that this thing here is, this object can be represented as a kernel. Really here, this is a slight abuse of notation, and so I write it out a little bit more carefully. The kernel of this map formally is the image of this by exactness. But the latter map is an injection. So what the post is doing is it's noting that since we have an injection, we can just identify an injection with its domain, because we're essentially just embedding the object in. That's what injective maps do. So he's calling that this arrow by just what the object is to start. That was the abuse of notation that was happening here as well. Well, I'm gonna rephrase. It's an abuse of notation in the sense, it's not an abuse, but it's an abuse to go from this to this. We've gone from an object to an arrow, but it's because we've identified an injective arrow with its domain. So because of that, we can now write it as, we can use, we've identified it as, we identify this object with its image of this monomorphism. I would identify that with the kernel by exactness, which gives us that the cohomology groups are these. They are the kernel of something that takes the ith part into the I plus 1th part, mod the image of something that takes the I minus 1th to the ith. This should look like cohomology to you. So this exactly tells us we can calculate the cohomology of an object F heuristically by taking an injective resolution. Because what did we do? How did we get injective resolution? Well, it's this. It's this top line here. What we did in the process of embedding injective objects into it and then embed into another injective and embed into another injective, that's the exact same as constructing via all this exactness. Remember, it wasn't trivial to prove these maps phi existed, but after we've done all it, we've noted that's the equivalent to defining this chain here of injectives, which tells us that the cohomology of the injectives kind of measures the failure for everything to have been captured from the prior step. Any questions on this? This, I think, is one of the most important things I could teach you. Hey, look, we finished that page right at 8:30. You got through all of that critical stuff, Robin.
Hooray. Okay, I'm going to bounce.
All right.
See you all Tuesday.
See you then.
See you.
Couple more. Acyclic resolutions. So one of the important properties we had there is that the cohomology of the injectives vanished, and then the homology of the projectives vanished. Turns out this is not trivial. This is actually very hard to prove. I leave the proof to Weibel. But assuming you can actually define derived functor cohomology in however you want, it turns out you don't really need to work with injectives or projectives. Those were just handy in our prior proof because I chose injectives because they were things that made the cohomology vanish. But if you think back to the heuristic proof I just went through on that prior page, all we really needed from the injectives is that they had vanishing cohomology. So we define acyclic resolutions as the generalization of that. They're just things that have vanishing cohomology. But importantly, injectives vanished for every F. That's why I just wrote the homology without F. With acyclics, all we really needed in the last proof, we fixed F at the start. So all we really need is that it vanishes for the choice of F. And that's important because they're generically injectives and projectives. It's hard to go much past that. In like a general setting, you can't. And I'll explain why in a second. But in general setting, those are the only things that for every additive functor are going to work, that are acyclic for every additive functor F. But there are things that are acyclic for specific functors, but not for all of them. And we can use those to calculate the cohomology of the functors they're acyclic for. And that's this theorem right here, basically. So essentially think of the last page as stating this result. This is a very important result. That we can use if these ENs are an acyclic resolution, then we can calculate the cohomology using those. So acyclicity does depend on F. I noted before that injective and projective resolutions are F acyclic for any left or right exact functor. Yeah, I guess it's not just additive because we need to be left to right exact in order to calculate derived functor anyway, because it needs to preserve a zero on one side. Otherwise, we get a dual infinite complex. And I guess you could try to do like bi-graded cohomology. That might work, but I don't know if you'll ever actually be able to calculate it because none of the stuff will ever terminate. You'd have to have some way to terminate stuff. But you could definitely define it. We have that the Hom functors are their acyclic resolutions are exactly the injective resolutions. That's an exercise in the book. I think I might have us do it. Dualizing, we have that the acyclic resolutions for the right Hom functor are the projectives. So because the did I mix these up? These might be backwards. I'd have to check. In any case, the important idea here is that because Homs are additive functors, in particular, or more particular, the left-right exact functors, the only things that could in general work for everything have to be injectives and projectives. because they're the only things that they are the only acyclic resolutions for the hum functors. So if we throw out the hum functors, you could then ask, if we ignore these, are there anything that's acyclic for all the rest of the functors? I don't know. So I don't know if like hums are universal. I imagine, I noted here, this is going to be some type of UNETA type result. I imagine there's going to be something you could say here about the UNETA, using UNETA embeddings if you cut out hum functors, but I'm not sure what. I didn't run through the proof of that. There are more specific things though, and these are very, very important. So we have things called flat modules or flat objects generally. Again, I leave that to Ada's talk. Flat resolutions are acyclic for tensors. All of this comes up from ideas I said earlier. Remember I said that the hum thing is exact if A is injective. The hum is exact if B is injective. These are exact if B or A are injective. So it shouldn't be surprising that if you throw in an injective object or projective on the other side, we get these resolutions are going to work. Sorry, I should have said if you plug in a flat object to the tensor stuff. I think I said that. More non-trivial examples are for paracompact Hausdorff. So this is something Anthony talked about. He talked about fine sheaves. Fine sheaves are an example of an acyclic thing with respect to the global sections functor. Also, more generally, flabby sheaves, also called flask sheaves, are also acyclic. Also, you have things called soft sheaves, which I didn't talk about here, and soft sheaves are also acyclic. There are a lot of things you can talk about that are acyclic with respect to global sections functor. Why do we have so many we talk about? These, you already know, calculate check cohomology. These are useful because they actually allow us to do calculations over, like, if you want to do calculations over schemes, you're going to be using flabby sheaves. These are even also used in complex geometry quite a bit, where often there you can use fine sheaves because it's paracompact Hausdorff, but it's often just much nicer to appeal to flask sheaves because of this statement that any sheaf has a canonical embedding into the flask sheaf of all possibly discontinuous sections of the Atali space. By repeating this, we can find a canonical flask resolution for any sheaf. So there's really a canonical flask resolution. That only depends on the sheaf structure. To get these fine sheaves to do this, I think, yeah, Wikipedia. So I copied this from Wikipedia to talk about this a little bit. Yeah, like we can take the constant sheaf on a manifold, we can resolve it via differential forms. So these fine sheaves for a manifold end up just being the space of differential forms. And they're going to be fine sheaves and they're acyclic. We also have things called Godemont resolutions, which are nice. Those are a type of flabby sheaf. Then these are the ones we actually usually do calculations with. And these are nice with differential forms. But the reason, say, in complex geometry, you might not want to work with it is you might want to be split into Hodge structures. And if you want to do Hodge decompositions of stuff, often it, like, you get generalized eigenspaces from your J complex, your complex structure. And it's often much nicer to just take the induced action on the space of forms you get via your complex structure and just construct a natural flabby sheaf structure on that, rather than trying to construct fine sheaf structures over it. It just gets too messy. Questions on any of that? Cool. Last slide, we're almost there. So examples, because I promised you guys examples today. I've given you some, I'll give you more, but I'll give you some really cool examples with sheaf cohomology, because the ultimate goal is, I said I would give a lecture on sheaf cohomology and Tor next. And you'll notice that in 2 lectures, I haven't actually done any sheaf cohomology or any Tor next. It is what it is. I've been trying to get there, but as you may have noticed, there's a lot of theory to build up. All right, so let A be an abelian group and let AX be the sheaf localized today, or the constant sheaf. So it's the sheaf that has stalks. It's why we call it AX, is because all of its stalks are A. Let S here is going to be for sheaf, not for singular. So for singular, I'm just going to write, nothing. It's just H dot. Check is going to be H with this little thing over the top, which I'll call the check because it's fun to use that terminology. I don't know what the symbol is actually called, but it's fun to call it a check. So it looks like a check mark. And then, so we have the sheaf one here, which is going to have an S. And note that I define the sheaf cohomology with respect to an abelian group A to, by definition, be the sheaf cohomology with respect to the constant sheaf at A. Same with check. This is standard abusive notation. Then the singular cohomology is just, it actually is within a abelian group. That's standard. And then we have the de Rham cohomology, which I put, it's really conventional to put dr here for it. That's standard notation in the literature. So let F be an arbitrary sheaf. The first statement we have is that if X is semi-locally contractible, what this means is like, it means you actually don't need all of locally contractible. You just, you just need that, like the local contractibility. The local map you would try to contract is actually like null homotopic. If that's true, then we get that the sheaf cohomology is equal to the singular cohomology. So we can calculate sheaf cohomology using singular, or vice versa. But I don't know why you would do the opposite. Unless you're in some complex geometry setting, I guess, where sheaf is more natural, which can happen. But those manifolds usually have obvious, it's usually faster to get the singular via simplicial stuff on those manifolds anyway. If X is, maybe if it's like a K3 surface, this would be useful. If X is paracompact Hausdorff, then we get, we can calculate the sheaf cohomology using check and vice versa. That was essentially what Anthony talked about in his lecture. So he proved this, sweetness. The proof of this using, I think Weibel gives a proof of this using something stronger than locally contractible. Uses locally contractible and vanishes on sections. Locally contractible is given in Goodmont's book. Semi-locally contractible is given in a paper that was like 6 years ago. If you're curious on the chain of proofs there. Originally, we also thought we needed paracompact Hausdorff. I think Weibel also consumes paracompact Hausdorff here. But again, we've proved we can remove all of that and just go with semi-locally contractible. Cartan's theorem. So if U is a basis for your space X, for which the check cohomology vanishes on each of the sets, and it's an open basis, obviously, then the sheaf cohomology equals the check cohomology. So this doesn't require it to be paracompact Hausdorff. It tells us generally for a space, we can, as long as we choose a nice basis, we can calculate the sheaf cohomology in terms of the check. Again, I noted this is 0 in positive dimension because obviously there should also be a dot there. I don't know why there's not a dot there. That's bad of me. It's technically the complex. Often people write it without the dot, but since I was writing it before, I just stuck with convention here. Then we finally have Loray's theorem, which you can, it's not technically a generalization of Cartan, like a specialization of Cartan's, but we usually think of it as a specialization of Cartan. We have Loray's theorem, which says that if we have a covering of our space, not necessarily a basis anymore, but just a covering, for which the sheaf cohomology vanishes on every finite intersection of things in the covering. Remember, finite intersections are very natural and like very basis-ish. But if it vanishes on all the finite intersections, then the sheaf cohomology equals the check cohomology of, importantly, the cover. So the difference between Cartan's theorem and Loray's theorem is in Cartan's, we have an X here. And in each of these, we had an X. And remember, this is defined to be, this is the colimit. This is defined to be the colimit over the U of this, over the check homology of these sections. So it's very nice that instead of needing to calculate a colimit like we would in Cartan's theorem, Larrey's theorem allows us to calculate it for just a specific covering. So this is really, really nice because it allows us to do calculations. Final little note here. Remember that right adjoints give left exact functors. Left adjoints give right exact functors. And it's, left exact and having right derived functors, and same with right exact having left derived functors, are essentially the same thing. If we want to find examples of things where we have cohomology, well, we might as well take adjoints. Every adjoint is going to give us exact functors where we can then calculate cohomology. So we know that Hom is adjoint. We know that the left Hom is adjoint to the right tensor, and the right Hom is right adjoint to the left tensor. So we get 4 natural functors. We get the ext functors, which are the right derived functors of the left Hom. We get what I call x star. This is not in the literature, but I call it x star because it is the, you think of it as like the dual map here. It's the right derived functors of this dual thing, the right Hom. Then we have, so this is left Hom, this is right Hom. We have that the tor is the left derived functors of the right tensor. And we have that tor star is the left derived functors of the left tensor. Finally, one asks, what is the relationship between ext and x star and tor star? There's some relationship between the Hom functors and the tor functors, but they're not the same. These aren't the same functors. Like the left and right Homs aren't the same. In this case, it's by contravariance, but there's deeper reasons for that. That they just can't be the same. And basically what Anthony was talking about earlier when Anthony and I were talking in response to Levi's question. But there's something called the balancing of tor and ext, which says that these are equal. Ext is equal to x star and tor is equal to tor star canonically. That will be a very, very important result that we can either read or talk about. This is a very long section of Weibel. It's very important and builds up a lot of the theory of ext and tor. I just don't have time to talk about it here. But why would we care about ext and tor? Well, here's some examples from Wikipedia just to titillate your mind. This is just for ext. I grabbed this off the page for ext. There's a bunch for tor as well. Like if we want group cohomology, that is just defined as Wikipedia is using x star to represent the complex of ext. They're not using the star like I am. They're using it just to represent all of the i's put together. But this is, so remember, because these are the same ext functor, but it's the ext functor of the group ring of Z mapping into your representation. If we want to calculate Hochschild cohomology, we do roughly the exact same thing. The idea is to take this and do it algebraically by replacing the group ring with this. Lie algebra cohomology does roughly the same thing, but instead of the group ring, we're using the universal enveloping algebra. Also, instead of Z, we of course need commutative rings mapping in because those are more natural in that context. And finally, using shift cohomology, if you were to write down what it for abelian groups, we can represent sheaves of abelian groups in terms of, we can represent the cohomology if you run through it in terms of the shift ZX. This is a really useful lemma. I probably should have talked about this. I only remembered about this in the last I was throwing this on the last page and I was looking through, but I actually put this in the notes as one of the first things. So I had forgotten to talk about this lemma and actually show this, but this is an important result that you can calculate sheaf cohomology using the ext functor. So imagine that as one of the things, like a 5 on this list that we often use. Is that if you want to calculate sheaf cohomology, you look at the locally constant z-valued functions mapping into your space, and you take the ext of that. So what are extensions of this sequence? Finally, I want to note that I talked about how you can often define derived functors generally. Kind of the first step towards that was Yoneda. He defined ext generally in a way that agrees if it has enough. It agrees with the definition, say Weibel gives, if it has enough projectives or enough injectives to define it. Remember, either of those is sufficient because those come from HOM. And one of the HOMs is projective resolutions, one is injective resolutions. So for X, you can actually calculate it from either. For Tor, you can only calculate it from one. That's a slight difference between Tor and X there already. And there are generalizations of this, what people have done past Junita. I sent a link to one earlier that proved that, in the cohomology of injective is always zero if you give the right definition of cohomology. There's a lot of ways to define it generally when there's not enough projectives or injectives.